Hi guys, Professor Stevens back again. I'm going to do another example for us. This is testing for symmetry, and let's read the problem. It says, without graphing, determine whether the following equation has a graph that is symmetric with respect to the x-axis, the y-axis, the origin, or none of these. So we will do each of the three tests one by one. Okay, so the first thing I want to point out is that the graph of an equation is symmetric with respect to the x-axis, the x-axis if the replacement of y with negative y results in an equivalent equation. Another way of saying that is that when you have the point x comma y on the graph, you also have x comma negative y on the graph. And so then, since you would have one input value assigned to more than one destination, that would not be a function relationship. That would just be an equation, but not a function. But you can have equations that have x-axis symmetry, even though they are not actual functions. So let's go ahead and do this test. So we'll start by, we're only going to be replacing the y with a negative. So we'll start by doing that here. And then we will simplify and see if we get, we get the exact same result, or you could say results in original equation. Okay, so therefore, or so, this equation is symmetric with respect to the x-axis. Okay, and what does this thing look like? You know, it said without graphing, determine whether it's symmetric, but let's graph it anyways just so we can confirm that this makes sense. So this equation is x squared plus y squared equals 13. And so there you can see that it is symmetric to the x-axis. If I choose any point on the circle, such as right here, you see the coordinates are 0, 11.58. Notice that changing the sign of y, so if I put 0, negative 11.58, that results in a point that is symmetric across the x-axis. We can also see that it has y-axis symmetry, at least it appears to, right? And also origin symmetry. If you rotate this thing upside down 180 degrees around the origin, it's going to look the same. So this is a circle centered at the origin, so it has all three types of symmetry, but we're still going to go through the three algebraic tests so that we can see how to do this without graphing. All right, so the next part here, let's do a test for y-axis symmetry this time. So the way to do this test is realizing that the graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x results in an equivalent equation. All right, so another way of saying this is that, just take this off entirely. We could also say that when you have x, y on the graph of the equation, you should also have, just changing the sign of negative x, comma y. Right, so you can change the sign of x and have the y value stay the same. So we will go ahead and perform the test. This time we're replacing the x So that negative x quantity squared results in x squared plus y squared equals 13, which is equivalent to the original equation. So it is symmetric. I'm just going to start abbreviation with respect to the y-axis. Okay, and the next part here, we're going to do origin symmetry. It says the graph of an equation is symmetric with respect to the origin if replacing both the x and the y with negatives will give you an equivalent equation. So we'll do that. Replacing them both at the same time, then simplifying. Okay, so again, we have an equivalent equation. The result after we simplify is the same as the original. Therefore, yes, symmetric with respect to the origin. All right, and again on the graph, I'll just show you. Remember with x-axis symmetry, we said if we have any one point on, or let me start by doing this point over here. So that point has the coordinates 11.58 comma 0. If I change just the sign of x, notice that the point is across the y-axis, still on our function graph, or it's not a function, it's an equation. It's still on the graph of the equation, just right across the y-axis. And for origin symmetry, if you change both signs, so let's say, well, using 0 is kind of hard. Let me figure out another point to try. Let's do this point right here. Move it there. Okay, so that looks like I'm trying to get the point to, it's not exactly right. Trying to get it right on there. There we go. Okay, so the point negative 11.4 comma 2, and then I'm also going to, let me zoom out. I'm going to see if this point E, if I go straight through the origin, will I have a point over here if I just change both signs of the coordinates? So instead of negative 11.4, I'll put in positive 11.4 for x, and instead of positive 2 for y, I'll put negative 2. And notice that right across the origin, you see we have that corresponding point on the graph of the equation. Okay, so this is finished. This actually had all three types of symmetry. And interesting about this one is the fact that whenever you have passed the test for x-axis symmetry and also passed the test for y-axis symmetry, then it will automatically mean that you will pass the test for origin symmetry. It doesn't work the other way around. If you have origin symmetry, that does not mean automatically that you will have x-axis symmetry and y-axis symmetry, but it does work in this direction. If you have both axis symmetries, it will be symmetric to the origin as well. So that's the end of this example. I'll go ahead and start a new video for a similar example. Thanks for watching.